Welcome. We are trying to solve this equation dou eta by dou tau is equal to del square eta by del z square, and I have made the assumption that eta is going to be only a function of z by root tau. And now I am going to define that z by root tau as y. I am also going to define d eta by dy as some p. Okay, these are just some definitions. So, I am going to say y is z by root tau. So, in other words, we are saying that eta is equal to a function of y, and d eta by dy we are going to call it as p. Now, let us take dou eta by dou tau and try to find out what it is. Okay. So, I want to take dou eta by dou tau and I want to find out what that quantity is. So, what is dou eta by dou tau mean? We are going to, the partial derivative means that the other quantity, other variable that you have, namely the z, which you are going to keep as a constant. So, I am going to write this dou eta by dou tau as follows: d eta by dy and dou y by dou tau, right. Why? Because I want to get the variation of eta with respect to tau, but eta is only a function of y, but y is a function of tau, the way we have derived, we have defined, right. Now, because we have defined y as z by tau, root tau, so if you take dou y by dou tau, that will be minus, right, because z tau power half minus half will be there, 1 by 2 will come, and z and then tau power minus 3 by 2. So, it will become tau and root tau. So, this is nothing but minus z by root tau is nothing but y itself. So, y by 2 tau. So, let us put it back here. So, dou eta by dou tau is nothing but d eta by dy, right, and minus y by 2 tau. Okay. So, let us for now let us keep it as dou eta by dou y and dou eta by dou y. So, I am going to say that when z is kept a constant, dou eta by dou y and dou y by dou tau is what dou eta by dou tau is. Okay. So, this is the left hand side of the equation. So, we have calculated dou eta by dou tau in terms of y. Okay. Dou eta by dou y, y by 2 tau minus with a minus sign is nothing but dou eta by dou tau. Now, let us calculate the right hand side of the equation. The right hand side of the equation is what? It is del squared eta by del z squared. I am going to use the same trick. I am going to say that it is dou by dou y and dou y by dou z, right. So, that is going to be my trick. So, let us first split it, dou by dou z of dou eta by dou z, this is what it is. So, let me keep this dou by dou z, and this I am going to write it as dou eta by dou y and dou y by dou z, right. Dou y by dou z, again we go back to our definition, y is z by root tau, which means dou y by dou z is nothing but 1 by root tau. So, 1 by root tau. So, we have dou by dou z acting on dou eta by dou y and 1 by root tau. 1 by root tau is, so this is partial derivative with respect to z. So, 1 by root tau can be pulled. So, you have 1 by root tau dou by dou z acting on dou eta by dou y, right. So, this dou by dou z I am going to use the same trick once more. So, what am I going to do? So, I am going to say dou by dou z is nothing but dou by dou y by dou z, right. So, I have now So, I have del squared eta by del z squared is equal to 1 by root tau dou by dou z of dou eta by dou y. So, I am going to use the same trick 1 by root tau, dou by dou z is going to become dou by dou y acting on dou eta by dou y multiplied by dou y by dou z, right. So, dou y by dou z again we know is 1 by root tau, and that is going to come here, and so it is going to become 1 by tau. This is going to become del squared eta by del y squared, and in all this process we have kept tau as a constant, right. So, we know that dou eta by dou tau was obtained as this quantity, we obtained it as minus y by 2 tau times dou eta by dou y. Okay. So, now let us equate these quantities, and we get, so minus y by 2 tau d eta by dy is equal to, we have derived the other quantity which is 1 by tau del squared eta by del y squared, okay, d squared eta by dy squared. And remember, we said that d eta by dy is equal to p. So, the tau tau goes away. So, you have, what you have is as follows, it is dp by dy minus yp is equal to minus yp by 2, right. D eta by dy is p minus y by 2 is equal to d by dy of d eta by dy. So, that is dp by dy. So, we have ended up with an ODE, right, in from the PDE that we started with. Now, this can be integrated. So, let us integrate it. dp by p is equal to minus y dy by 2. So, if you integrate that equation, what do you get? You get logarithm of p is equal to minus y squared by 4 plus some logarithm of a, that is a constant. I am taking it as logarithm because now I am going to exponentiate, so it will make it easy for me. So, then I get p as some a exponential minus y squared by 4, but p is nothing but d eta by dy. So, let us integrate it one more. Eta is nothing but integral a exponential minus y squared by 4 dy. This is the solution we have obtained. Remember, eta itself was a scaled quantity. So, now I can go back and substitute for eta, and what do I get? Eta was nothing but c minus ci by c naught minus ci is equal to integral a exponential minus y squared by 4 dy. And let us recall, what did we define as y? We defined this quantity z by root tau as y. So, y squared is nothing but z squared by tau. Like I said, we took the normalized diffusivity to be 1, but that 1 is sitting somewhere here. Okay. So, this is what I said in the other context. I said x squared equal to dt, right. So, this is z squared by d times tau. So, it is the same quantity. Okay. So, this is the solution. Sometimes, for example, if you look at a textbook like Porter and Easterling, this solution is what is written. It says C is equal to C I, okay, plus C 0 minus C I and this A exponential minus y squared by 4 dy. This A has to be determined. So, this is part of the error function definition, it is a 2 by pi or something like that, but I have left it as A itself for now, and you can look at so Porter, for example, you will know the exact value for this quantity, and this is known as the error function without this constant exponential minus y squared by 4 dy. So, typically this quantity is tabulated and you look up the tables and you use the values, and that is how you calculate composition as a function of position and time, right. So, for any given any position you can calculate y, which is a combination of position and time, and you can put it here and then you will get the solution corresponding to that quantity. And this is plotted. So, we will do it. We do not need to look up tables for getting error function. Octave has a function called error function, I suppose. So, we will use that and we will try to plot the solution and so on. Okay. So, this is something that we will do later when we start going back to Octave and doing some of these things numerically. But the point that I am trying to make is that there are two ways in which we have solved the diffusion equation. It is a partial differential equation. So, you try to convert it into ordinary differential equations and solve. Variable separable is one method, using dimensional arguments and using some transformation of variables to reduce it to a ordinary differential equation and solving it is the second approach. This approach gives us the error function solution, which is meant for semi-infinite case, as they are described sometimes in the literature. And the other solution that we saw by variable separables is basically the homogenization solution, that is what it is called. So, this solution that we have obtained is very important. For example, if you are looking at carburizing, decarburizing, or if you are looking at doping a semiconductor with some dopant, and those kind of situations where you keep the one end of your material at some concentration. For example, carburization, you keep it at some carbon concentration and your material is at some other carbon concentration and you carburize it, okay, or decarburization. That happens because outside the carbon concentration is less than what your steel has. So, from the surface it starts losing carbon, and so these kind of solutions are obtained. Sometimes diffusivity is also measured by putting together like it's like a rod, and then somewhere in between you put a radioactive material, okay, very thin slice of radioactive material. So, it is like two semi-infinite rods put together. So, the error function solution on both sides, that will give you the spread of the radioactive material into the material in which you are trying to measure the diffusivity. So, using then the error function solution, you can back calculate the diffusivity. For a given time, you take slices away from this source point and you look at the carbon whatever concentration of the radioactive material. From that plot, you try to calculate, you know the distance, you know the time for which it was there at that temperature. So, at that temperature, what is the diffusivity can be obtained using similar experiments. All this is explained in Porter and Easterling, for example. So, what we have done is to derive that solution. So, in Porter and Easterling it is written, this is the solution. So, we have just tried to derive the solution and see how we get this solution in the first place. Okay. So, the next step is of course to go and solve the classical diffusion equation numerically. So, in the next part of this lecture, I will do the legwork that is required to solve the equation numerically. Actually solving it numerically, we will do it in the next lecture. So, thank you.